Leetcode 417, Pacific Atlantic water flow. It's a medium problem, definitely not easy. As you can see, the description is quite lengthy, and I think that's the only thing which makes it relatively hard to other mediums. So you have to read a lot, think about it for a bit, and then come up with a solution. And at least in my case, the solution is also a bit lengthy relative to other mediums. Yeah, so I know that sometimes some companies are giving this problem in job interview when you have very short time to do everything, including reading, understanding, creating your solution, discussing with the interviewer, and so on. And for this particular problem, it might not be maybe not feasible. Like I don't want to say that it's not feasible, but it's definitely harder than other mediums. But don't get discouraged. I think that it's a very good problem for training purposes. Yeah, and you should definitely study it in your own time and think about it and try to come up with your own solution. So here is the description. There is M times N rectangular island that borders both the Pacific Ocean and Atlantic Ocean. Yeah, so we have Pacific, Atlantic, something water flow. And rectangular island, meaning that we will be dealing with grids or matrices or lists of lists, as they call it in Python. And M times N means that those grids or matrices might not be square. Yeah, so you may have a different number of rows and different number of columns. You should not expect a square. And the next thing is the Pacific Ocean touches the island's left and top edges. Yeah, so from left side and from the top we have this grid or this rectangle, and from left and top we have Pacific Ocean, and from the other two sides, right and bottom, Atlantic Ocean touches the island's right and bottom edges. The island is partitioned into a grid of square cells. Yeah, so we have simply like each element in this n times n rectangle. Yeah, you have those sub-elements which are called cells, and the cells themselves are square, meaning that they have the same size or the same area, and but there is one property in which they differ between each other. And here it is. You are given an m times n integer matrix heights. Yeah, each of them will have a height, and each of those cells, and we have to read it from this again m times n integer matrix called heights, where heights on the index r in a given row and index c within this row, the column from the row, represents the height above sea level of the cell at coordinate r and c. Yeah, so this is a little bit hard, but very explicitly stated that we will have those cells, and each cell has this single property called height. And we can identify which height belongs to which cell, of course, just simply by taking the row and column coordinate, yeah, or x and y coordinate, as you may call it as well. Yeah, so sometimes they use different notation for that. And the island receives a lot of rain, and the rain water can flow to neighboring cells directly north, south, east, and west. Yeah. So what are the neighbors of a cell? Well, we have a grid. Maybe let's try to draw something quickly. Let's remove this big one, just the small ones, and like this. Yeah, each square here is a cell, and then each cell can have or has certain neighbors. And let's say that we are right now considering the blue cell. Let's make it blue like this. And what are their neighbors? As they say, it's north, south, east, and west. Yeah, so there might be at most 4 neighbors. Now let's make them yellow. So those diagonal, let's say cells which are also close to the given cell are not considered neighbors. At most it has 4, but if you take one from, let's say, the corner, then it will have just 3 neighbors. So it can have less than 4. And that's it. Water can flow from any cell adjacent to an ocean into the ocean. And that's the part that I missed. I was looking for if cell's height is less than or equal to the current cell's height. So if this one has greater height than that one, so it only can flow to the neighbors, but then the next condition is that it can only flow in one direction. If your neighbor has height which is less than or equal, or less than or equal, then your height, then the water can flow. So for example, if this cell had height of 5 and this cell had height of 8, that means that the water can flow in this direction. But if this cell had height of 12, then the water could flow like this, but it couldn't flow like this. That wouldn't be allowed. And that's what they mean by this. And the other cells are not even considered, since those are not the neighbors. And the next thing, the island receives, that's what we read right now. And the last part is return a 2D list of grid coordinates result, where result of I is a pair. So at the end, we will also return a list of lists, but each inner list within this list will be just a pair of 2 coordinates. So just the coordinates which represent a valid flow denotes that the rainwater can flow from cell Ri and Ci to both Pacific and Atlantic Oceans. So we have to figure out if there is such a connection of neighboring cells starting from a given cell that we will reach either Pacific Ocean, which is here. Let's make loop. Or Atlantic. Did I say it correctly? Yes. So from this side is Pacific, and from this side is Atlantic. And here is Atlantic. And if we can construct such a path, then we should consider all the cells on this path valid, and then return their coordinates inside this list of pairs as a result. Into either to the Atlantic or to the Pacific. And that's one of the things that makes this problem a little bit, maybe not more complex, but at least it takes more work to solve, because you have to consider those 2 options separately for Pacific and Atlantic, and in the end you have to return the intersection, because we care only about such a path that goes to both Pacific and Atlantic Oceans. Okay, so here is a full example. We have such grid, 5 times 5. In this case it's square, but it doesn't have to be square. And the input heights are as follows. So they are given as rows 1 by 1. So the first row 1, 2, 2, 3, and 5, and so on. Then this is the next row, and this is the next, and so on. And so that's the input, and there's only one input, those heights. And from this we can extract both the number of rows, number of columns, and the property called height for each cell. And the output is the following. So the first valid cell is 0, 4. Where is the cell 0, 4? That's the row 0 and column 4. First is row 0, 1, 2, 3, 4. And what is the explanation? It can go to Pacific Ocean and Atlantic Ocean. Why? Because this cell itself borders both Atlantic and Pacific, of course. So the path contains only one cell. The next one, 1, 3. Okay, so here is 0, 1, and then 0, 1, 2, 3. This one is also a valid one. And how does it go? 1, 3 goes to 0, 3 to Pacific. Yeah, so it goes like this. Okay, from 4 to 3 it can go and goes to Pacific. And from 1, 3 to 1, 4. Okay, it can also go like this because it doesn't have to be less. It can be less or equal and goes to Atlantic. And so on and so forth. We will not read all of them since it's just simply too many options. Yeah, note that there are other possible paths for these cells to flow to the Pacific and Atlantic Oceans. Yeah, and those paths may not be even unique. Yeah, so there might be multiple ways in which you can go from one cell to both oceans. And the second example, here you have single element, so the island consists only of a single cell, and then of course this cell borders both Pacific and Atlantic Ocean, and the path contains only the cell. Yeah, so in the output we are returning coordinates, and in the input we have heights. Yeah, and the coordinates of course are the row and the column for given height. So that's it about the description. Already big chunk behind us. So now we have to think about how to solve this problem. Maybe let's copy this. And first thing that we have to notice is that it is search problem. And there are two common algorithms for search, DFS and like this, BFS. Yeah, so the depth first search and breadth first search. And in this case, I can already give you a spoiler. At least in my take, it doesn't matter whether we use DFS or BFS, but in my experience, usually BFS takes a little bit less memory, at least the implementation that I prefer. So either way, we will have to go through each cell. Yeah, whether we use DFS or whether we use BFS, we will have to consider each cell at least once, but we will not want to use them more than once. Yeah, so we have to think about a way such that we will traverse this graph or this grid. And the grid, every grid can also be thought of as a graph, and we will have to validate in each iteration of the traversal this specific condition about heights. Yeah, so grid is also a graph, and cell within a grid would be something that in the language of graph theory we would call node or slash vertex. Yeah. And the adjacency, meaning those neighboring nodes on the neighboring cells, is something that we would call here edges. And of course, it is undirected, meaning that if we can go from one cell to another, we can also do it in the other way. And unweighted, and there are no weights. It could be that a grid has weights in the case where, for example, some cells would be walls or something like this, but in this case it's not unweighted. Yes, and the time complexity for BFS is generally V plus E, and the number of nodes plus the number of edges. And in this case, BFS. In this case, we would have how many nodes? M times N, yeah, and exactly M times L cells. So we can write it down. Maybe like this. And how many edges? For each cell we will have at most 4. So 4 times M times N. Exactly equal, and that would be like almost equal since some have less than 4. Yeah, but either way, this can be simplified to O of M times N. Since plus we only take like the bigger part and we drop the constant, and since both of them are M times N, then in the end time complexity is M times N. And the next thing that we want to write down is this: less than or equal. Yeah, and that's our main condition. And now we will have to create a BFS loop, which is usually we are using queue. We are enqueuing some initial nodes, like in the simplest form, you just have one starting point, but here we will be starting from each node next to the Pacific Ocean for one, and for the second, each node bordering with Atlantic Ocean, and then we will be checking in a queue each of their neighbors for each of the starting cells one by one. There will be a queue. We will be adding them to the queue. First, the starting nodes, then their neighbors, but only if they meet this condition. And we will continue up until we have no more nodes, or there are no nodes which satisfy this condition. Yeah, and we'll have to do it first, check for the Pacific, then for the Atlantic, and in the end, we take the intersection and return the indices. And so you can write it down, create BFX loop for both Pacific and Atlantic Ocean nodes or cells separately, and try to enqueue as many nodes or as many cells. Let's stick to the cells. As possible, using neighbors. Neighbors. How do you spell it? Like this, neighbors. And verifying the condition. Verifying like this. And that's our condition. And in the end, return the intersection between both groups. And so that's high-level overview of all the steps that we need to do. And now we can discuss the details. So let's create a structure called reachable. And inside BFS loop, you usually have to mark in some separate structure visited nodes to not revisit them multiple times. And we will use this reachable grid, which will also be a list of lists. And let's say we consider an island which has 9 cells, like here, 3 times 3. Then the reachable will be exact map of that. We will have 3 lists inside a list, so it will be like a 2D list of lists, like this, and it will store Boolean values for each cell. And so initially it will all be set to false. Like this. And we will have to have some starting points. As we said, the cells bordering Pacific Ocean for the Pacific, and for the second group we'll have cells bordering Atlantic Ocean. And we will update, so we can write it down here. Like here is like more specific steps of what happens inside the first step of this high-level overview. So we'll create reachable grid and initialize all to false, and then n will be its size. And then update cells corresponding to starting coordinates corresponding like this. And so let's say we will do it for Pacific, then the first those 3 and those 3 will be updated. So first is all false, and then it will get updated to true, 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 and true. And then we need another structure queue. We can call it just a queue for BFS, where we will be enqueuing the cells that we still haven't checked. So at the beginning, it will simply be those cells. So enqueue all starting coordinates like 0, 0, and 0, 1, 0, 2. I have those 3, then here is 1, 0. And we could separate this part, by the way. And 2, 0. Like this. And that will be initial queue, and then we'll have a loop while queue not empty. And inside this loop, start another list here. Pop first pair or just pop the pair from our queue. Yeah, and then check all its neighbors. And for each, check if the condition holds. Let's maybe do like this. If so, then enqueue first and update reachable. Yeah, and that's it. That's like the whole strategy. And so this will happen inside the BFS. It has to be repeated separately for both Atlantic and Pacific Ocean. And in the end, we'll do the intersection between both the results, and we should have the answer. So right now, maybe let's do first example for 0, 0. We will have, let's maybe add some values here as well. Let's say 1. 5. Why it's not? Okay, like this. I was wondering why it wasn't in the middle. And here, let's say, don't know. Don't like it. 30. Why it's not rising? Okay. Let me just write like this. 30. Here, maybe 7. Okay, I'm getting crazy. Let me just copy and paste this. 7 and 7 and 7. Let's do like this. And first, either way, we consider this one, which is 1. Yeah, and so we are inside the loop. We pop the first pair, 0, 0, which has the height of 1. Then we check all its neighbors. So the neighbors are the following: this one, and that's it. Yeah, and both are enqueued already. So both are already set to true. Here, true and true. So we don't have to do anything. We simply remove it from the queue, and that's it. And then we check the next one, 0, 1. And this one has the following neighbors. This one we have already checked, that and that, and the 8. Yeah, so 1, 30, and 8. Yeah, and for 8 and 30, both the water can flow into my current cell. So both of them are valid, but 30 was already enqueued. Yeah, so we can only add this one, which is 1 and 1. Yeah. Yeah, and we remove it and add it here and update here to true. And that's it. And we'll continue this process up until we have reached every element, or up until we have no more cells to try because there is no possible flow. And in the end, we will have the results stored in this reachable data structure, which is simply a list of lists, and each Boolean value corresponds to given cell. Yeah, so this one has a index 0, 0, which corresponds to the cell on the index 0, 0, and that's it. Okay, so let's try to convert it to Python. So first things first, we always have to check if the input is valid, even. Yeah, so they can have they can provide us with an empty or almost empty matrix of heights. So if not heights, or sorry, not and or not, or either if the heights is completely empty or the first row is empty, then we cannot do anything. We need to have at least one element like here. Now we can store m and n, and we can get it from the heights. So m will be simply, because we have this number of rows times number of columns, will be the length of heights, and n will be the length of the first element inside heights, which is the first row, and it has n columns inside. Then we can have some helper function for all the possible directions. So left, right, and here top and bottom. And it so this is bottom, this is top. I see. And that's it. And now we can concentrate on the heart of the solution, our BFS helper function. And so we'll need starting or start coordinates. Hope I haven't misspelled anything. Coordinates, and inside we'll create reachable, which will be, of course, false times the number of columns for underscore in range of number of rows. Yes, that's it. Then we need to have a queue as well. And I think that's something that we have to import from collections, import the queue. And while queue is non-empty, we will be doing something with it, and in the end we can return reachable. So the queue can be created from the starting coordinates, and for each row and column inside start coordinates we will update corresponding reachable row and col to true. Yeah, and while queue is non-empty, we will have row and col from queue pop left. So we'll pop, and now we have to go through each neighbor. So for direction, in our directions, we will have a neighbor row and neighbor column equal to row plus, we can already unpack it here. So just make it like dir row, dir col, like this. And that's how we can check each neighbor. And now we have to have some long ifs. So if, first of all, it has to be valid row. Yeah, so just this part. Row has to be between 0 and m, and column has to be, and here plus of course, between 0 and m. Yes, it has to be unvisited yet, so reachable on the position neighbor row and neighbor column has to be false, and we need to have our heights also compared. Yeah, so the height here we can check. Height will be taken from heights on position row and row and column, and the height has to be less than or equal to the one from our neighbor. Yeah, those are, I think, all 4 conditions that we have to satisfy. And if so, then we can update reachable and enqueue new cell. Push and here neighbor row and neighbor column. Like this. So now how many starting points do we have? Since we will need to have starting coordinates. Pacific starts will be equal to 0C for C in range N plus R0 for R in range M. So this will be this. Each one has x0, 0, 0, 0, yeah, and C in range N, and R will be this. Those are the starting points for the Pacific, and for Atlantic, something similar. We will have so here we will have C instead of 0 we will have m-1, yeah, and here we will have n-1. Here the last, here is the first, and here is the last. Cool. Okay, so now we have to call BFS on both of them. And Atlantic starts, and store the result, Pacific result equals, and Atlantic equals to this. Yeah, and now we will have to create the final result, which will be like row and column for row in range length of M for column in range of N, and I call it call, and if both results are set to true, so if the given position row and call, and the same for Atlantic. So I for sure made some spelling mistake or something like this, so let's try to run it and correct one by one. Invalid syntax, index out of range, line 34. 4 are in range. Okay, and here as well. Okay. Indentation. Push should be append. I always have problem between those append, add, push, and so on. Can't remember which one belongs to which data structure. And yes, and len. Yeah, those are already the lengths. Those are the integers. Yeah, so we don't have to call length again. We call the ones here. Let's see. Okay, both cases correct. And we beat 96%. So it wasn't that many mistakes. I thought there will be more. I'm positively surprised. By the way, and we beat 96% when it comes to the runtime and 65% when it comes to the memory consumption.